All right, so we're going to look at what's called the dot product. Now, the dot product has a lot of interesting applications in physics and maths. The dot product is basically a measure of how much two vectors are pointing in the same direction. It sounds a bit vague, but we're certainly going to drill down into this idea. But let's just for now imagine that we've got two vectors, A and vector B. Vector B is this longer black vector that's underneath this blue vector. And what we're saying is we're going to wonder how much these vectors are kind of pointing in the same direction. If A was down here, we could say that they're pointing in exactly the same direction. And you can see that the dot product is larger when they're pointing more or less in the same direction. When they're not pointing in the same direction at all, the dot product goes to 0. In fact, when you're at 90 degrees, the dot product is 0. And then if they're pointing in opposite directions, you're going to get negative dot products. So this is sort of the motivation for what we're going to look at, because we're going to prove why it's the case. I'm just going to put this line in here, and this is a little bit of an oversimplification, but one way you can think about it is how much is vector A projected onto vector B? But then you just need to keep in mind that you're going to scale that up or scale that down based on the size of those vectors A and B. In this case, though, as you said, these vectors have a size of 1. So as we project vector A onto vector V, this blue vector is the size of the dot product. So you can see that this blue line at the moment is taking up 62% of the entirety of the black vector. So the dot product is 0.62. As we move it around, it gets larger. Now, again, don't be confused in thinking that it's just that simple. Remember, we've got to take into account the size of these vectors as well, but that can sort of give you an indication of what we're trying to do when we go ahead and try and prove this dot product. Okay, so proof of the scalar or dot product, more commonly known as the dot product, sometimes known as the scalar product. Here it is. If you've got two vectors, vector A and vector B, you take the dot product of them, and that's equal to A1, B1 plus A2, B2 plus A3, B3. Okay, geometrically, the dot product between two vectors is equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by cosine of the angle between the vectors. Okay. We're going to explain where all this comes from in a moment. A few key results you need to be aware of is what's called the cosine rule. So when you're working with triangles, the cosine rule relates the side lengths and the angles, and it says for some triangle A, B, and C, the side length A squared is equal to B squared plus C squared minus 2BC cosine of the angle. So you've got to keep that in mind, and you also need to be aware of the magnitude of a 3D vector. So for some vector V in space pointing at the coordinates V1, V2, V3, the size of that vector is equal to the square root of V1 squared plus V2 squared plus V3 squared. That might look a bit daunting, but that's just Pythagoras in 3 dimensions. You have applied Pythagoras to the length of that vector, and this is what you get. Pythagoras actually works in all dimensions, 3, 4, and into the nth dimension, right? So let's see if we can make some sense of it. What we're going to do is we're going to consider two vectors. We've got this vector A, which is equal to A1 multiplied by I, where I is the unit vector in the x direction, plus A2 multiplied by J is the unit vector in the y direction, plus A3 multiplied by K, where K is the unit vector in the z direction. So we're in 3 dimensions, right? 3 dimensions with my hand here. Okay, and then we're going to take another vector B, and this is also pointing in 3 dimensions. And these A1s and B1s, these are all just coefficients. So you're basically scaling up or scaling down the size of the magnitude of the vector in the x direction with A1, and similarly scaling up or scaling down the magnitude of the vector in the y direction with A2. Okay, we're going to create a triangle, and let me explain. So we've got this vector A, got some other vector B. Okay, I encourage you to get out a pen and paper and do some vector addition here, but I can assure you that this vector from here to here, from the top of A to the top of B, would be the vector A minus the vector B. And that's just some vector addition stuff you need to be aware of. But yeah, definitely think about that. And we're also going to put some labels on this. We're going to call this O, we're going to call this B, and we're going to call this point A. Okay, we're also going to put some angles in. Let's call this angle here theta, and then we've got all these other angles here. Okay, you might be wondering, we were just talking about vectors in three dimensions, and then I just drew something in 2 dimensions. So when I was doing this, I found that a bit perplexing, but I just want to show you that that's allowed to be done. So let's just come over to 3D space, and let's pretend we've got 3 semi-random points. I've sort of just made up these points. One happens to be at the origin. These A and B I could have put anywhere. And what I claimed was that we could create some vectors and get a triangle that we could represent in 2 dimensions. And let me explain. There we go. So you can see we've got our triangle, and the question is, well, can we represent that in 2 dimensions? And I think the answer is yes. If I get this angle right, you can see that that triangle is on a plane somewhere. It's kind of there. So what we can actually do, if I click on the plane through 3 points, click on that, that, and that, you can actually see that that triangle sits nicely on the 2-dimensional plane. It's a bit hard to see, but there you can see it there. So pretty cool. And so that's what basically we've done back over here. We've represented a 3-dimensional vectors in 2D space, and we still get a triangle that's valid. We're just sort of on the plane. Okay, now it's going to get tricky. Let's have a think. Basically, to take this triangle, we're going to take this triangle, we're going to apply the cosine rule. So we get vector A minus vector B squared. So the magnitude of this vector squared, because we take the side length squared, is equal to the magnitude of B squared plus the magnitude of A squared minus 2 magnitude of A, magnitude of B, cosine of this angle in here. Now, definitely go and watch the video on the cosine rule if that's confusing, but basically we've just applied cosine rule to this triangle that we've created. Okay, this line looks confusing, but let's break it down. We've got these vector A and vector B. The magnitude of the vector A minus vector B, well, that's just going to be its constituent components in each direction squared, taken away from one another. So remember, A1 represents the magnitude of the vector in the x direction for the first vector, and B1 represents the magnitude of the vector in the x direction for the second vector. So we take them away from each other. That will tell us the magnitude of the resultant vector. So we get that for each of those situations. So A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 squared. Okay, on the right-hand side, let's look at vector A squared. We take the magnitude of vector A and square it. Now remember, the magnitude of the vector is given by this, Pythagoras. The magnitude of vector A is A1 squared plus A2 squared plus A3 squared. But then we're squaring it. So the square root and the squared go away, and we're just left with A1 squared plus A2 squared plus A3 squared. Okay, similarly for B, the magnitude of B squared. We get this. Okay, and this stays the same, minus 2, magnitude of A, magnitude of B, cosine of the angle that's created. Okay, now you just need to recall the following. Recall that when you binomially expand each of these, A1 minus B1 all squared, you expand it binomially, you get A1 squared minus 2A1 B1 plus B1 squared. Now what happens is this A1 squared on the left-hand side that we would get if we expanded this would cancel with this A1 squared on the right-hand side. So that term is going to cancel out. And nicely enough, this B1 squared on the left-hand side will cancel out with this B1 squared on the right-hand side. And that would happen for all of these. The same thing would happen. So what's actually going to happen is the only term we're going to be left with from each expansion is this middle term, minus 2A1B1, minus 2A2B2, minus 2A3B3. And then all of these are gone as well. And you're left with just this right-hand side, just this part here, minus 2, magnitude of A, magnitude of B, cosine of the angle. Okay, we're almost there. You'll notice here that -2 is a factor. Take -2 out as a factor, and you're left with this. And what we're going to do is we're going to divide through by -2, so they cancel out. So you just have with A1B1 plus A2B2 plus A3B3 equals magnitude of A by the magnitude of B, cosine of the angle. Now, that is our dot product. This was our definition of the dot product. A1B1 plus A2B2 plus A3B3, but we can see geometrically that it also equals the magnitude of vector A by the magnitude of vector B multiplied by cosine of the angle between them. So quite a mouthful. I did promise that we would look at some applications of this. A classic application of the dot product in the physics world is work. So you calculate work by multiplying the force by the displacement. Force and displacement are both vectors. So we could say if you want to work out the work done on an object, you multiply the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between them. And maybe we'll just bring it back here for a moment to sort of tie it all together. Imagine this was a force vector and this was a displacement vector. If we had these at 90 degrees, the force that you're applying and the direction that the object is moving are at right angles to one another. So no work is being done. And that's how we calculate work. If we had a situation where the force was, say, moving in this direction, but the displacement was in that direction, this could be like a frictional force. Imagine you're pushing a box, your force is applied in one direction, but the displacement is in the other direction. So you would get a situation where you get a negative dot product. And yeah, similarly, once we start getting back to here, we get the dot product being large. So this is when the force that you're applying and the direction that it's moving, or the displacement, the force vector and the displacement vector are pointing in the same direction. So you're doing a lot of work. All right, that was heavy, but hopefully that made some sense. Good luck with all your studies, and I'll talk to you soon.